It's important to take a minute to understand where some of the more important concepts that we have in chemistry come from. Things like the electron is a negative charge and the nucleus has protons and neutrons, and these have all come from fundamental experiments. The first one we want to talk about came from Lavoisier in 1789, and he was able to show the law of conservation of mass. And by that we mean that in chemical reactions or physical transformations, matter is neither created nor destroyed. And we're going to see this in our reactions, that the atoms that we put in have to equal to the atoms that we get out. And this, of course, isn't true for nuclear reactions, and that's a completely different topic. But we're going to use this idea to balance reactions later on. Overall, this means that we really can't gain or lose anything during our reaction. If we put a carbon in, we're going to get a carbon out. And this is something that we take for granted now, but back in the beginning, somebody had to come along and actually prove that this was true. Part of this idea of the conservation of mass really started the idea that matter was made up of these small indestructible particles. So the idea of an atom started to come through from this, and all that they're doing is rearranging atoms. And we're going to find out that that's fundamentally true, that during chemical reactions we're taking atoms and just rearranging them to go from reactants to products. Then Proust came along in 1797 to give the idea of definite proportions, which says that for a given compound the mass ratios are the same. So if I have 100 grams of water, that 100 grams of water is going to contain 11.19 grams of hydrogen and 88.81 grams of oxygen. Therefore, the oxygen to hydrogen ratio is 7.94. And this ratio of oxygen to hydrogen is going to be the same for every sample of water. And this was the beginning of the idea of molecules. So this implies that water is combined in a certain way with oxygen and hydrogen. So that's where that came from. Dalton in 1808 came up with the idea of atomic theory, and this is really when they began to understand that elements are made up of individual atoms. And we take the idea of definite proportions another step and say that water is combined of 2 hydrogens and 1 oxygen. And this defines what water is. And if we change those ratios of hydrogen to oxygen, say we have H2O2, we're not talking about water anymore. We're talking about something else. Also, this really came to the idea that elements don't change during chemical reactions. They only change how they're bonded. So once again, we put a hydrogen in, we get a hydrogen out. If we put a hydrogen in as a reactant, we're going to get a hydrogen out as a product. How that hydrogen is bonded and what's it bonded to, that can change. J.J. Thomson in the late 1800s discovered the electron, and what he was using is a cathode ray tube. And what that does is it was emitting particles, and these particles were independent of the composition of the material that they were originating from. So this meant that this was a fundamental particle and it was coming from different sources. And he was able to show that this particle has an electrical charge, and that electrical charge is negative, and that the mass is quite small compared to that of the atom. Millikan in 1909 was able to determine the charge of an electron, and this is kind of a famous experiment called the Millikan oil drop experiment. And what he did is he made oil droplets by an atomizer. An atomizer just takes a liquid and sprays it into very small particles. And he was able to give those oil droplets a negative charge by bombarding it with ionizing radiation. And we'll talk about what ionizing radiation is later. So he was able to give the oil drops a charge, and then he was able to suspend these oil drops between 2 charged plates, one with a positive charge and one with a negative charge. And he would adjust this charge until the oil droplets would halt from their fall from gravity. So he would suspend these oil droplets between the positive and negatively charged plates, and then he looked at the electric field that it took to cause this to happen, to cause the oil droplets to stop from falling from gravity. And from this he was able to determine the charge on the electron to be negative 1.60 times 10 to the minus 10th coulombs. And he was also able to determine the mass of the electron to be 9.10 times 10 to the minus 28th grams. And probably one of the more important experiments, Rutherford in 1909 was able to come up with the theory of the modern idea of the nuclear atom. And so once again, the nuclear atom is still just a theory. There's tons of evidence to prove this. But once again, it had to come from an experiment that allowed this to come into being. So the modern idea of the nuclear atom came about from an experiment. So prior to Rutherford's experiment, scientists believed in matter being composed of what was called the plum pudding model. And that just said that the matter was made up of a cloud of positively charged things and negatively charged things kind of floating in a mixture. And being a good scientist, what Rutherford did was he tested this theory of the plum pudding model. And he did this by taking a gold foil target and shooting alpha particles to it. Alpha particles are a type of radioactive decay that we'll talk about in the radioactivity section of this book. But an alpha particle is a type of radioactive decay, and they didn't really know it at the time, but they know now that it is made up of 2 protons and 2 neutrons. So they knew that the alpha particle was quite dense. And he fired these alpha particles at the gold foil, and the idea was that if it was the plum pudding model, the alpha particles should go straight through, no problem. There should be nothing inside of the matter to actually stop something as dense as a alpha particle. So if the plum pudding model was true, the alpha particles should have passed through the gold foil undetected. And what he found out that the positively charged alpha particles were being deflected by the foil. So alpha particles, we'll find out later, are positively charged, but some of the alpha particles were going through the foil, but some of the alpha particles were actually being bounced back, and some of them at 180 degrees. And this really said that the plum pudding model wasn't true. And this goes back to the idea of scientific theory. So they had this model that they were using, and Rutherford did an experiment that showed that that model wasn't true. And what scientists do at that point, they say they have to come up with a new model. So they needed to come up with a new model that explains Rutherford's experiment. And where this came up, what this produced was the idea of the nuclear atom. So Rutherford was able to determine from this experiment that most of the mass and all the positive charge was centered in a very small region called a nucleus, and it was these nuclei that were bouncing these alpha particles back. And also part of this, most of the volume of the atom is empty space, and so this is where the electrons live. Most of the volume is empty space, most of the mass is condensed into the nucleus. Also, that the negatively charged electrons are outside of the nucleus and the positively charged protons are inside of the nucleus. So it makes sense that the protons are in sort of a large blob that was able to reflect the alpha particles, and the electrons were somewhere else, and those didn't stop the alpha particles. So we also learned, and this came a little bit later, that inside of the nucleus are neutrons, but that was something that they discovered later, and they figured out that neutrons were neutrally charged.